In this lesson, we are going to cover converging and diverging lenses. We are going to focus on ray diagrams in this lesson. Let me first show you the shape of converging and diverging lenses. Here we have a sphere of radius r1, and here we have another sphere of radius r2, and here is the cross section of the two spheres. This cross section is the shape of a converging lens. On the other hand, we have a sphere of radius r1 and another sphere of radius r2. If we fill the space between these two spheres, we are going to get a diverging lens. As you see, this side of the diverging lens has radius r1 and this side has radius of curvature r2. Similarly, this side of the converging lens has a radius of curvature r2 and this side has a radius of curvature r1. By the way, converging lenses sometimes called convex lens, and a diverging lens is also called concave lens. These are the shapes of convex lenses and these are the shapes of the concave lenses. As you see, the convex lenses are thicker in the center. Look at the center is thicker than the edges. Here also the center is thicker than the edges. Here also. Similarly, for the concave lenses, the middle is thinner than the edges. The edges are thicker than the middle. The edges are thicker than the middle. As you see, it's same for all of the type of the lenses. Also, we show the convex lenses like this, and we also show this is the illustration for the concave lenses. In ray diagrams, many textbooks use this type of illustration of the convex and concave lenses. Let's draw some special rays in concave and convex lenses. First of all, let's have a ray parallel to the principal axis of the lens. This is a converging lens, and the ray will refract through the focal point. Another light ray from the focal point will move parallel to the principal axis. A light ray to the center of the lens will move without changing direction. This one also will move without changing the direction. A light ray passing through the center and it comes to the lens. This is a converging lens, and it will also move back. It will move toward the center after passing through the converging lens. Let's look at some special rays in concave lenses. I mean diverging lens. First of all, a parallel ray will refract from the lens. Its extension will appear to pass through the focal point. This is the parallel light ray to the principal axis, and it will move toward that direction, but its extension will pass through the focal point. Similarly, if you send a ray to the lens, this diverging lens, and this ray is aiming the focal point, and it will move parallel to the principal axis. As you see, lenses has two focal points, and this one also have two focal points. Let's look at the special rays in diverging lenses. A light ray to the center of the lens will not change the direction. And the other one, if a light ray is aiming the center of the converging lens, it will move such that its extension will pass through the other center. So the light is aiming this center, but after refracting from the lens, its extension will pass through the other center. Okay, what if we have an arbitrary ray? Now assume this is an arbitrary ray. This is coming to the lens, and then after passing through the lens, how it is going to move? What will be its refraction through the lens. This is a converging lens. To see the direction, this is the incident ray and this is the refracted ray, we need to first draw a parallel line from the center of the lens, which is parallel to the incident light ray. Okay, this one and this one are parallel to each other. Then we draw a perpendicular line from the focal point and it crosses with this parallel line. And this point is called the second or the other focal point of the lens. So the incident ray will pass through this new focal point if this is a arbitrary ray, and you can draw its refraction from the lens like this. What if it is a concave lens or diverging lens? An arbitrary ray to the lens, first we draw a parallel light ray to the incident ray, and then we draw a perpendicular line from the focal point and we get another point f prime. And now this refracted ray, the extension of the reflected ray will pass through this point. So this is the ray diagram for an arbitrary ray from a concave lens. Let's look at some examples. The first one is a parallel light ray to the principal axis is going to refract through the focal point. Then now this light ray, this is the refracted ray, but it is an incident ray for the lens on the right. So it is coming through the focal point. It means it will move parallel to the principal axis. Now let's look at this one. A light ray aiming the focal point. It is moving toward the focal point, but it will refract parallel to the principal axis. Remember our ray diagrams. Now a parallel light ray to this lens is going to refract such that its extension will pass through the focal point. By the way, in this example and in this example, let's call this the first example and this is the second example, and the focal length of the lenses are equal to each other. Here their focal lengths are also equal to each other. Let's look at this one. Again, we have the lenses, their focal lengths are equal to each other, and this is a converging lens, this is a diverging lens. A light ray, as you see, it is coming through the center. Why? Because 2f is the center. Then it will move to the 2f. Here is 1f and this is the second f. It is going to refract and it will move toward that point. But this is now an incident ray to this diverging lens, and now it is moving toward the focal point of the diverging lens, and this point was the center for this lens, but now it's also the focal point of the diverging lens. So since this light ray is moving toward the focal point, it will move parallel to the principal axis. So the last example is, here we have a lens, a converging lens, and here we have another converging lens, and their focal lengths are f1 and f2. We are asked to find the ratio of f1 to f2. So as you see now, a light ray is moving to this lens and then it is moving to this point after refraction. This is the incident ray. This distance is x and this distance is also x. This means that, remember our previous ray diagrams, when light ray is coming from the center, it moves to the center again and these distances become equal to each other. That's why f1 will be equal to x over 2. And now this is a refracted ray and it's an incident ray for the second lens, and as you see, it is coming from this point through this point and then it is moving parallel to the principal axis. It means that this point is the focal point of the second lens. So f2 will be equal to x. Once you divide them, you are going to see that f1 divided by f2 will be 1 over 2. Okay, thank you for listening.